Okay, class, so this is question number 7 found on page 197 of your textbook. So what we have is it's a simple conservation of energy question that involves a pendulum, 85.5 centimeters long, which is held at rest. So that's 24.5 centimeters in amplitude. So it says neglect friction and air resistance. Use energy concepts to determine the maximum speed of the pendulum after release. So I think most of you can see that if we were to release the pendulum from rest at this point, it should swing down to some lower point. And of course, you can see that at this point over there, you should have a decrease in gravitational potential energy, which must therefore translate to an increase in kinetic energy, thereby helping us find the speed at that point. And I think the first thing you have to realize, though, is that in this case, you have to ask yourself, well, what exactly is the height that we have at this point with respect to its lowest point? And I think most of you can see that we have a right angle triangle over here. So we have some kind of a right angle triangle, and if I were to find this side over here, if you want to find the length of that side, I think most of you can see that all we have to do is use Pythagorean theorem. So we have the hypotenuse side, 85.5 centimeters. We have this side down here, 24.5 centimeters. So by using Pythagorean theorem, what we actually end up with is, do a quick calculation, so you end up with a value of about 81.9 centimeters. So 81.9 centimeters is that length. So let's think about this for a second. If my pendulum were to fall to its lowest point down there, what you're basically telling me then is that the difference between this point and that point must be the difference between 85.5 centimeters and 81.9 centimeters. And with a quick calculation, it does turn out to be about 3.6 centimeters as the difference in height. So what we're going to do is do a little calculation involving the law of conservation of energy. Before I do that, let's just label a couple of things here. Let's pretend that the pendulum takes a path that looks something like this. Okay, so it's going to start off at this point over here. I'll label that as point A, and I'll label this point down here as point B. And let's just zoom out once again. And let's use the law of conservation of energy to see if we can solve what speed we have at the bottom. So again, we know that the sum of all my energy at point A must be equal to the sum of all my energy at point B. If you take a look at point A, the only form of energy we have at that point, because we know that it's at rest at that point, it must have gravitational potential energy. So let's just write down mgh at point A. And if you take a look down at point B, the only form of energy we have is kinetic energy. And again, that's assuming that this is, of course, our reference point, the lowest point. So you should have kinetic energy, which is 1/2 mv squared, and that's, of course, at point B. You may notice that they never give us the mass of the pendulum, so again, it doesn't really matter because we know that the masses stay constant from one point to another. So let's plug in the variables that we know so far. 9.8. The height at point A with respect to the lowest point is 3.6 meters, and all that's got to be equal to 1/2 speed at point B squared. So if I solve for the speed at point B, let's just do a quick calculation. And you should end up with a speed of about 8.4 meters per second. And that's your answer. That should be the speed at the lowest point. It's your maximum speed because if it's at its lowest point, it's going to have the least amount of gravitational potential energy and therefore the greatest amount of kinetic energy. Okay, so I hope that helps you guys out. For those of you who asked about this question, there are a couple of you. It is a little bit of a review from last year, but hopefully it makes some sense now, and we'll see you all tomorrow. Thank you.